Welcome everyone to the sixth lecture of the series. We would be learning about flexural loading in this lecture. The contents are shear and moment in beams, the load shear and moment relationship, the shear and moment diagrams, flexural formula, shear stress in beams, and the deflection. So first of all, there are two types of loadings. So one is concentrated loads, that is the load is applied on discrete points that are being separated. But in distributed load, points loading is been concentrated on each and every point throughout the length of the beam. Now, if we want to determine the bending moment and shearing force at any point in a beam, which is subjected to either concentrated or distributed or both loads, what we need to do is we need to first treat that beam as a single body so that we can find the reaction that it supports. Then we would cut the beam at a point, let us say that point is C, and then draw two free body diagrams, one for section AC and one for section CB. Now we apply the equation of equilibrium so that we can find the values of V and M. So in section AC, as you can see, we can find value of V, which is equal to be P1 minus RA, and then we can find the corresponding moment by using force into the perpendicular distance. The same thing we have done here, but here we have represented those uh, shear and bending moment graphically. So these graphs are known as the shear and bending moment diagram. So here we have an example where concentrated load has been loaded on a given beam with given dimensions, and we need to draw shear and bending moment diagrams. So first of all, what do we do is we draw the free body diagram and treat it as a single body to find the reactions. Once we do that, we cut the beam at different sections. So the first we cut it at A, then we cut it at between A and B, then we cut it at B, then between B and C, then again at C, and then again at C and D. And we apply the equations of equilibrium at all these sections individually, and we calculate the shear and bending moment. And then we plot them in a graph. So finally we have the shear and bending moment diagrams. Okay, so from the graph, we can also develop a relation among load, shear, and moment. So if we equate it, we find that area under the graph is also equal to the integral of that u upon the certain limits. So using that, we can develop a relationship between shear and bending moment, which is shear is equal to the differential of bending moment with respect to length. So V is equal to dm by dx. Here is another example which you can take it as an exercise. The answer is also attached. Now we have shear stress in beams. So basically it's just the derivation using those integrals. So the concept to be understood here is, first of all, you need to understand what is a neutral surface. So a surface which suffers no deformation or deviation is known as neutral surface. Usually it is at the centroid of the beam, and all the deformation that take place are either above that surface or below that surface. And then if we apply the equations of equilibrium, we can find that sigma x is minus of my by I, where sigma is the stress, m is moment, y is the distance between the point and the neutral surface, and I is the section moment of inertia. So now how to find the section moment of inertia? So for a beam, section moment of inertia is 1 by 12 bh cube, where b is the breadth and h is the height. If is hollow, we find first, if, like, for example, we are given a beam of cross section which is in figure B. So if we want to find the section moment of inertia, what we do is first we the find the section moment of inertia for the whole rectangle, and then subtract it from the hollow part so that we can find the effective S. So now, due to the stress developed, there is always a strain. So in beams, that can be seen in the form of deflection. Now, how do we know that how much has the beam deflected? So we can know this from the elastic curve. And the basic fundamental concept about the elastic curve is d2y by dx square is mx by ei. So if we want to find the elastic curve, we need to double integrate it. And if we are double integrating these equations, we would have two constants. So in order to eliminate those two constants, we have certain conditions for certain beams. So this condition is as visible in the figure. So at some points y is 0, at some points dy by dx is 0, and this is different for differently supported beams. It can be simply supported or overhanging or cantilever. So now here we have an example that a load P is applied on the cantilever beam, and we need to find the equation of curve. Okay, so first we double integrate it and just apply the conditions so that we can find the values of C1 and C2, and then we place back to get Y. So this equation number 5 is our answer. That's all. Thank you.